All right, so we made it through number 15. Let's go to number 16. Number 16 says, is it possible for one sound wave to cancel another? Yes, through destructive interference. Remember we talked about the headphones and how there's a speaker inside the headphones and that sound cancels out the sound from outside the headphones and you get destructive interference, which is a canceling of the sound waves. Okay, number 17 says, explain how you can produce a low-pitched note on a guitar string. So the first thing you want to do is you want to change the length of the string. You want to make it longer. Longer string creates a lower pitch. Because if you look at F is equal to NV over 2L, F2L over N is equal to V. So if I keep the speed in the string constant, if this gets greater, this has to go down. A lower frequency is a lower pitch. Part B says the tension in the string. A lot of tension makes a high clinking noise. Lower tension, you get a lower pitch. Lower pitch. And then C says thicker string. The thicker the string is, the lower the pitch. Think about if you get a real skinny rubber band and you stretch it real tight, it makes a real high-pitched plinking noise. If you take a real thick, fat rubber band, it's not going to move as easily, and you're going to have a lower pitch. Lower frequency, lower pitch. How does the interference of sound relate to the beats? Well, the change in, or the difference between the two frequencies. Let's call this difference in the frequencies causes beats. Okay, number 19. If you are standing at a track meet and are far from the starter, you'll notice the smoke from the start gun before you hear it fire. Why? Because the speed of light is much greater than the speed of sound. So the light gets to our eyes before the sound gets to our ears. Speed of light much greater than speed of sound. So the light gets to our eyes faster than the sound gets to our ears, is what I said. Okay, number 20 says, if the handle of the tuning fork is held solidly against a table, the sound becomes louder. Well, that's the sounding board question that we already talked about, and that was on, let me see. Where's the sounding board? Number 10, so we already talked about that. Now the next thing says, how will this affect the length of time the tuning fork keeps vibrating? Well, it's not going to vibrate for as long because it's giving all of its energy away. Energy conservation says that nothing can be created. You can just change forms, so the kinetic energy of the tuning fork is going to be dissipated by causing the sounding board to vibrate. Okay, then we have some problems. Now, there's not any Doppler on here, but I can promise you there's a Doppler problem on the test, so make sure you look over the Doppler stuff. Alright, 21 says, what is the beat frequency when I have a 494 tuning fork and a 496 tuning fork sounded together? So the beat frequency is the difference between the two, so I'm going to say 496 minus 494. Beat frequency is 2 beats. Number 22. 22 says, an oceanic depth-finding vessel surveys the ocean with an ultrasonic sound that travels at 1,530 meters per second. And water. Now, I'm not sure if the question's saying 3 seconds down and 3 seconds up. That's what I assumed. So I said, well, speed is equal to distance over time. So if I want to know the distance, I'm going to take the speed of 1,530 and I'll multiply it by 3 seconds of time. And that's going to give me the distance. So that's a 0, a 9, a 5, a 4. So that's how the deep ocean is at that point. When I write something like this on the test, I would promise that I would tell you it takes 3 seconds to go down and 3 seconds to come up. So you would be very clear about the time situation. A cello with a string 0.75 meters long has 220 as its fundamental, so F is 0.75 meters. The fundamental is, oh, that was kind of goofy. Should have said that's the length, I'm sorry. The fundamental is 220 hertz. And if it's the fundamental, then N is equal to 1. And we're asked to find the wave speed. So if F is equal to NV over 2L, then F2L over N would be equal to V. So frequency is 220. 2L is 0.75. N is 1. So that's my length. So if I solve for my length, I get, when I did it, I got, no, I'm sorry, I'm solving for my speed. Wake up, Miss Walker. So my speed when I did it was 330 meters per second. All right, 24. 24 says an open organ pipe has a length of 2.30 meters. And the speed of sound in air is 340. So part A asks us to find the fundamental frequency, so N is 1 if we're talking fundamental. So F is equal to NV over 2L, and it's open pipe, that's why I picked the 2. So 1 times 340 over 2 times 2.30 is equal to, well, if I take 340 and divide it by 4.6, when I did that I got 73.9. That's my fundamental. B asks you for the first harmonic. That's also the first harmonic. And then C asks you for the third harmonic. So if I multiplied 73.9 by 3, I got 221.74 hertz. Okay, number 25. Number 25 says, a lightning flash is seen and 10 seconds later the rumble of thunder is heard. Find the distance to the lightning flash if the speed of sound is 340. So I said distance is equal to speed times time. My speed was 340. And it took me 10 seconds to get that rumble. So 3,400 meters is my distance. All right, 26. 26 says, find the wavelength of each of the following frequencies and assume the speed of sound to be 343. So I said, well, wavelength is speed over frequency, 343 over 252. So if I divided that, I got 1.36 meters. Part B, wavelength is speed over frequency, 343. And that frequency was 20 hertz. So that was 17.15 meters. And then C said speed was 343 and frequency was 20,000 hertz. So when I divided 343 by 20,000, I got 1.715 times 10 to the minus 2 meters. And then the last thing says, what is the relationship between wavelength and frequency? They're inversely proportional. So speed is equal to frequency times wavelength. These two are inversely proportional. As this goes up, that has to go down. 27. 27 says a string 100 centimeters long, L is 1 meter. When plucked, produces a fundamental, so N is 1, and the frequency is 200 hertz. And then they start asking me all kinds of things about if you put the string and hold it at 25 centimeters from one end. Well, I can't answer that until I find the speed of sound in that string. So F is equal to NV over 2L. So 2LF over N gives me V. So 2L is 1 meter. F is 200 hertz. The fundamental is 1. So my speed of sound is 400 meters per second. Now what I can do is I can go back and find out, okay, so if the length is now 25 centimeters and the speed is 400 meters per second, what can I do to find the frequency? Well, F is equal to NB over 2L. So N is 1, B is 400, 2L is 0.25. So in that short piece, it's going to be a frequency of 800 hertz. And then it says, what about the piece that's left at 75 centimeters long? So L is equal to 0.75 meters. B is still 400. And the new frequency is going to be NB over 2L. So 1 times 400 over 2 times 0.75. And if I do that correctly, the frequency is 266.67 hertz. Okay, so I'm going to stop there, and then I'm going to finish up 28 and 29. Actually, 28, I think I'll keep going. Yeah, okay, so let's do 28. 28 is pipe closed, so F is equal to NB over 4L. So we have the length is 1 meter. N is 1 because we're going to do the fundamental. 340 is our speed of sound in air. And L is 1 meter. So our fundamental is 85 hertz. That's also our first harmonic. Now, part C says, what is the second harmonic? Well, the second harmonic occurs at third when it's vibrating 3 times as fast. Because remember, with closed pipes, you only get 1, 3, 5. So if this is my fundamental, this would be the second harmonic, 3 times 85. And if I multiply 85 times 3, I get 255. Please study.